Hello everyone, welcome to Mastering Math and thank you for watching. This video series has been designed and developed by the Elsa McGill Learning Center Scholars in the Faculty of Engineering at Carleton University. My name is John O'Keefe and I'll be your host for this high school math review. I recently graduated from Carleton University with a Master's of Applied Science in Aerospace Engineering. In addition, I've worked in the LC Center for the past 6 years helping first-year engineering students such as yourselves. This math review is intended to refresh your memory based on high school math topics that you'll be seeing throughout first-year engineering courses. This is meant to be a supplemental resource, so it's not meant to replace any of your in-class learning activities. New students are expected to view this video series as well as read the accompanying PDF document in the link below, and then please revisit this as needed throughout the academic term. And with that, we'll get started. So in this video, we're going to cover rate of change. This is a good intro for derivatives. It's also used in the data management course, ECOR 1042, for the finite difference method. So we'll start out with the average rate of change, then we'll get into the instantaneous rate of change, and finally we'll get into applications, which is that finite difference method. So starting off with average rate of change, if we have a function here defined as f of x, and then we're going to look for the rate of change between 2 points. So here and here. And we can draw a secant line between these 2 points. Secant line is when you have 2 separate points and it's just finding the slope of that line, the rate of change between that line. That is a secant line. So we can define the rate of change of this as the rise over the run of this line. Where your rise is going to be shown right here. So that's going to be over on this side. And your run is your corresponding x values down here. Where this is defined as x1, this is x2, and then this would be the function defined at x1 or the function defined at x2. So now we can add these in. So the rise is f of x2 minus f of x1, and then all divided by x2 minus x1. And that's what our rate of change is for a secant line, the average rate of changes. So we'll do a quick example here. So example, we have our function is defined as f of x is equal to x squared plus 5x. And then our points, we want to know what the average rate of change is between x is equal to 5 and x is equal to 2. So this will be our x2 and this will be our x1. So now if we want to solve for our rate of change, we just apply this expression. So rate of change is equal to, so our function defined at x2, which is 5, minus our function defined at x1, which is 2. And then we would divide all this by what the run is. So this would be 5 minus 2. Now solving this out, we can actually substitute our expressions in. So our rate of change is equal to, so we have 5 squared plus 5 times 5 minus 2 squared plus 2 times 5. Then this will be all divided by, again, the 5 minus 2. So now actually evaluating this expression out, we have rate of change, solving this, and we get rate of change is equal to 12. And that's what our average rate of change would be between 5 and 2 for this function f of x is equal to x squared plus 5x. So that's average rate of change. Now we'll get into instantaneous rate of change. So here we can have a very similar f of x. This could be anything again. And then if we want to determine what the rate of change is at this point, we can draw a tangent line. A tangent line is where you're looking for the rate of change at a single point. Tangent means it's only touching the curve at a single point. So if we want to look for what the average or the instantaneous rate of change of this is, we can define this point here. This is at x now, because we only have, it's only touching at a single point. And then we have the point where it's evaluated at would be then f of x. So if we want to look at for what the rate of change of this line is, again, it'll just be the rise over the run. And the problem with this now is we only have one point defined, f of x and x. But what we do is we place a second point infinitely close to it at a distance h away, where h is almost 0. So what we're going to say is we have f of x, sorry, I should put this in blue, keep this in blue. We have f of x plus h minus f of x divided by, so the difference between these two, the run, would then just be h, the difference between these 2 points. And then we said h is almost 0. So we're going to apply the limit as h goes to 0, where the limit is just basically saying it's almost 0, but not quite. If you sub in 0 into this expression right away, you're going to get 0 over 0. So that's undefined. So basically that means you need to do more work to the expression. So typically you have to simplify the expression before you can actually substitute the limit in. So now we'll do an example of this. So if we want to find example 1, our function is going to be defined as, we have the exact same function as before, which is x squared plus 5x. And now we're going to find it at a point rather than 2 points. So we're just going to find it at x equals 5. We're going to find what the instantaneous rate of change is. So now using our expression, we have rate of change is equal to the limit as h goes to 0 of a rise over a run. So this will be f of 5 plus h minus f of 5 divided by a run, which in this case, it's now just h. So now actually substituting our expression in, and then we're going to simplify. About that. So rate of change is equal to the limit as h goes to 0 of, so now we have 5 plus h squared, and this should all be in blue as well because it's still the numerator here. So this is 5 plus h squared plus 5 plus multiplied by 5 plus h, and then minus just our expression. So then this will just be minus 5 squared plus 5 times 5. All divided by h. So now expanding all this out and then simplifying, we're left with, as h goes to 0 still, and we're left with h plus 15. So now we can substitute the limit as h goes to 0 because this is no longer going to give us 0 over 0. The rate of change is then equal to 15. That's our answer. So now we'll do a second example. So our second example, we have the function f of x is equal to 3x squared plus 2x plus 9. And now we're not going to give it a point. We're going to find what the instantaneous rate of change is for the entire function f of x. And this is known as the derivative by first principles. So now evaluating this, we have the rate of change is equal to the limit as h goes to 0 of our function f of x plus h minus f of x, all divided by our run, which will be divided by h. Now, substituting our expression in, we have limit as h goes to 0. So now we're going to substitute plus h into this expression. So we're going to be left with 3 times x plus h squared plus 2 x plus h plus 9. And this is all brackets minus our function. So this is just 3x squared plus 2x plus 9. Then this is all divided by our run, which is h. Now evaluating this expression, so we're going to expand the brackets here, FOIL it out, and then simplify. So then we're left with the limit as h goes to 0 of 6x plus 2. Sorry, 6x plus 2 plus 3h. And now we evaluate the limit. This is no longer going to give us 0 over 0. So then we can evaluate the limit. So the rate of change is equal to 6x plus 2. That would be our answer. And if you know derivatives already, you could easily check this. The derivative of 3x squared plus 2x plus 9 is 6x plus 2. But it's just good practice. And then finally, so that's instantaneous rate of change. We'll get into applications now. And the main application, as I said, was finite difference method. So your finite difference method, it is determining the rate of change of a function. And this is going to be equal to f of x plus delta x, where delta x is a very small change in x, minus f of x, all divided by delta x. So as you can probably tell, this is a very similar expression to our instantaneous rate of change. And the reason for that is this is used for computers to evaluate the instantaneous rate of change of a function using an actual computer in your data management course. So essentially, computers can't solve an analytical expression like we're solving with the limit here. But it can approximate it using a very small value of x. So this could be 0.001, etc., whatever. The smaller value of x you use, the more precise your answer will be. And it all depends on your scenario. Sometimes it doesn't matter how small it is, and sometimes it matters a lot more. So now we'll solve an example using this one. So our example here, we have our function is defined as f of x is equal to x squared. So just an easy function. And we want to find what the instantaneous rate of change is at x equals 5. And we're going to apply finite difference method here. Imagine you're coding this in Python, essentially, which you will be. And we need to choose a delta x. So I'm going to choose a delta x equal to 0.01. So I'm going to say this is sufficiently small for me to get an accurate answer. You could use a smaller delta x if you wanted to, but for me, just evaluating this expression, this is what I'm going to use. So now to determine what the rate of change of this is equal to your f of 5 plus your 0.01 minus f of 5 divided by what your delta x is. So this is 0.01. Now subbing in our expression, we have 5.01 squared minus 5 squared divided by 0.01. Now we can just evaluate this. Our rate of change here is equal to 10.01. So this is very close to the actual answer, which is 10. If you use a smaller value of delta x, you'll actually get a closer to 10 answer. And that's it for the rate of change this week. If you have any questions, feel free to email the emlc@carleton.ca, and definitely check out the link below with the PDF document. There's more examples as well as some practice problems for you to solve. All right, thanks for watching, everyone.